in the last lecture we discussed about the necessity or the idea which prompted the researchers to shift the design principles from elastic to that of a plastic one, where the researchers or the designers wanted to make use of the additional reserve strength of the material which is available beyond the first yield point, and first yield point formation is generally because of the presence of residual stresses in especially in particular in material like steel or marine steel. So one can think of using the or utilizing the reserve strength which will enable more or less a complete utility value of the material, because I can stretch the material to the maximum load carrying capacity. There are two reasons why the designers wanted to shift parallelly or transit parallelly from elastic design to ultimate load design, where the following: one, the load carrying capacity can be enhanced from yield value to an ultimate value, at the same time the ductility feature of the material can be used fully, so that it is a guarantee that the material will not fail until the strain reaches the strain at ultimate value, or the ductility ratio is expected to fulfill the reserve strength of the material. So these two were inherently prompted the designers to shift the design principles from elastic design mechanism to that of a plastic design principles, provided this system can be applied only for material and structures. Material should have enough ductility and the structure should be statically indeterminate. As the higher order of indeterminacy is envisaged in the system, the benefit is far and far, because essentially the ductility factor or the ductility capacity will try to redistribute the moments from highly stressed section to the next highly stressed sections. So we will continue to see what would be the methodology by which I can estimate the moment carrying capacity of a simple section. So what I will do is, we will consider a beam subjected to pure bending. The beam should have at least one axis of symmetry, it can be of any cross section, that is not important. The cross section should at least have one axis of symmetry. So let us say I have a beam, I subject this beam to pure bending. So the beam will start bending, and of course there will be an axis which is very important to discuss. We will talk about this axis slightly later. So I am applying pure bending or moment at the ends of the beam. So the beam is bent and keep on increasing the moment, and the beam will be keep on bending. Let us say the beam has any specific cross section of any shape. These are the extreme fibers of the beam. Now the beam will have two axes actually. One is what we call as a neutral axis, which I call as neutral axis, where the strain remains 0. The other one is a new axis which we call as equal area axis. I am drawing an yellow line here. I call this as equal area axis. So initially the strain in the extreme fiber and correspondingly the stress in the extreme fiber will remain lesser than the yield value, that is the first case. As you further keep on increasing the moment at the ends, the extreme fibers will reach the yield value, that may be the next stage. Now, if you further increase in the moment at the ends of the beam, then you will see that some section of the cross section will be yielded. So, you will find that till this point and till this point you will find the strain or stress will be equal to sigma y, and this will remain still elastic. I can call this as what I call as an elastic core. So, the section will start remaining elastoplastic because there is an elastic core present, there is a plastic core also present in the section. As you keep on further increasing the moment, a stage will come ultimately where the entire section will get plasticized. So, there is a very interesting thing happens here. When the entire section gets plasticized, the stress will move in this format, where if I call this as my compression, this as my tension, because you see here when I am applying the moment at the end, the bottom fibers will elongate and the top fibers will compress. So, I can say this is compression, this is tension. So, I am marking compression and tension in the extreme top and bottom fibers. So, interestingly, the neutral axis will start shifting downward and will merge with a new axis called equal area axis. Okay. So, the neutral axis will shift downward to merge with equal area axis. So, I can say now this is fully plasticized section, fully plastic. This is elastoplastic. Of course, these are all completely elastic. Since I said it is equal area axis, obviously C should be equal to T, that is why it is called as an equal area axis, though the figure may not show that because the section is not uniform. Okay. Let us say this is my compressive force C, this is my tensile force T, and this acts as a CG, let us say y bar 1, this acts as a CG as y bar 2. I can redraw this figure slightly in a different manner, saying that let us say the section has got fully plasticized. I can call this is my total compressive force, this is my total tensile force. I can call this as my y bar 1, this as my y bar 2, where C is the total compressive force, where T is the total tensile force, and this is nothing but my equal area axis. So, I can call this as G1, this as G2, where G1 and G2 are the centroid points of the compression and tension area respectively. So, I can call this as A1 and this as A2 and so on. While loading the section from the extreme fiber to reach elastic yield value to that of the entire plastic section, we make certain assumptions. Material obeys Hooke's law, until the stress reaches, I should say, first yield. So, on further straining, stress remains constant at sigma y and remains constant. The upper and lower yield points in tension and compression fibers are same. Material is homogeneous and isotropic. In both elastic and plastic states. Plane transverse section that is a section which is normal longitudinal axis of the member. So, what do you understand by this? I have a member, this is my longitudinal axis of the member, I cut a section which is perpendicular to the longitudinal axis of this member. If the member has a breadth b, the section will also have a breadth b, which I am drawing somewhere here, let us say b. So, this section is normal to the longitudinal axis and this remains plane, okay, this is plane. Okay. Will remain plane and normal. To the longitudinal axis of the member after bending also. There is no resultant force acting on the member. The cross section is symmetric about an axis through which its centroid passes. And is parallel to the plane of bending. You understand what does it mean? Suppose I am trying to locate a centroid of this section about which the section remains symmetric, and that point lie on a plane which is parallel to the plane of bending actually. Okay. No shear force acts in the section, only bending moment is considered. The beam is subjected to M only, no shear force is considered. Most importantly, every layer is free to expand and contract and remain independent with respect to the adjacent layer. What does it mean? In a given cross section, if I say this may equal area axis about which the centroid is located, the section remains symmetric. I take any fiber, in each fiber along the cross section are having freedom to independently expand and contract. There is no friction between the layers. Okay. Having said this, I will retain this figure. Let us now derive the moment carrying capacity of this beam, which is the plastic moment carrying capacity. So, we already said C is equal to T, the total compression should be equal to total tension force in the cross section, and we already know C is equal to sigma y into A1, and this is also equal to sigma y into A2, because I say A1 area of compression as you see from this figure and A2 is the area of tension as you see from this figure, they should remain same. Why I am using sigma y? Because it is an assumption that once the stress reaches the yield value, thereafter the stress remains constant at sigma y. Okay. So, this implies that A1 is equal to A2, which implies that this is nothing but A by 2, because A1 plus A2 is total A. Let me take moment about moments of forces about equal area axis, about this axis. Okay, they will form a clockwise couple. I should say that that moment should be equal to C into y bar 1 plus T into y bar 2, which is sigma y into A1 into y bar 1 plus sigma y A2 y bar 2. I should say sigma y A by 2 y bar 1 plus y bar 2. So, this gives a similar comparison to me, saying sigma y and Zp is Mp, which is also equal to M ultimate. When I introduce a new symbol Zp, Zp is called plastic section modulus, which is given by A by 2 y bar 1 plus y bar 2. Now, how do you define a plastic section modulus? You can see here Plastic section modulus has two components, one is the area, other is y, it is a product. Okay. So, I am taking moment of the area about an axis which is separated up and below or top and bottom or compression tension by y bar 1 and y bar 2. Okay. So, I should say that plastic section modulus is defined as the static moment of the cross section above and below the equal area axis. It is also called as the resisting modulus of the fully plasticized section. Therefore, plastic moment of resistance, which is also equal to the ultimate moment carrying capacity of the being, is nothing but sigma y into z. That becomes a very interesting and simple derivative. I can compare this with elastic moment carrying capacity, which we all know is nothing but sigma y into z. To make it very clear, I may even write Z E here, does not make any difference. This is called simply the section modulus, which you all know. Okay. So, this is known, this is a new one which we have derived for. Now, I can also find a ratio between these two moment carrying capacities, that is MP by ME. Okay, I can find that, which I will call as a shape factor. I will introduce that. Now, we have taken a general cross section whose area is A, and we found out y bar 1, y bar 2, we said A by 2, etc. Now, for a standard cross sections, can we find these values and try to find out what is actually ZP? Can we find out that? We will take up a standard cross section, maybe start with a rectangular cross section. Okay. Then we will work out some other cross sections and see how can I really find out the plastic moment carrying capacity of a given cross section readily. Okay. So, I will take up an example of a rectangular cross section. I will take up a rectangular cross section. Let us say the breadth of the cross section is B and depth of the cross section is H. I am drawing an elastoplastic section which has an elastic core depth as E, where E is depth of the elastic core, and of course, the stress here remains sigma y. So, the section is elastoplastic, E denotes the depth of the elastic core, as shown in the figure. Now this section has got two moment carrying capacities. One is the capacity of the elastic section alone, other is the capacity of the plastic section. There are two, okay. Let me call, let M1 be the moment capacity of the elastic section and M2 be the moment capacity of the plastic section, and we all now agree the total moment carrying capacity of the section M total will be a sum of M1 and M2. Let me now estimate M1 separately and M2 separately and get M total, which will be the total moment carrying capacity of the elastoplastic section, which I can call simply as M. Okay. Now to find M1, that is the moment carrying capacity of the elastic section. So M is going to be simply stress multiplied by the first moment of the area, which is nothing but half base height, because this is E by 2, and the CG of this area will be somewhere here, which is going to be, if I call this as E by 2, this value, and this is, let us say for example x bar, and this value will be equal to 2/3 of x bar. Okay, I am writing it there, of E by 2, which is going to be 2/3 of E by 2, and such sections are there, one above the axis, one below the axis. Okay. So can I multiply this by 2, because it is symmetric. So when I simplify this, I will get sigma y b e square by 6. Is that all right? So I am calling as M1. Let me call this as equation 1. Now I want to find M2. This I will do slightly in a tricky manner. What I will do is, if my section is fully plastic, if my section is fully plastic, then I will get the z value as b h by 2. Okay. This is h, you see from the figure, this is h, and of course this is b. Okay. B h by 2 and h by 4 of twice, that is a fully plastic section. Is it okay? Which will become b h square by 4, that is fully plastic. I can call this as Z1, which is fully plastic. But the section is not fully plastic, it is partially elastic also. It means I now have a section whose stress distribution is also elastic, which has the elastic core equals E. Now what I do, I replace this part by dotted line. Can I do that? It is going to be equal, no? One is C and one is T, I can equal. So I find only this part and see what happens. So, I can call that as Z2, which will be B into E by 2, B into E by 2, because this is E, into E by 4 of twice which will become B E square by 4. Is that okay? But my real section is a combination of these two. So, I can now say, I will remove this, M2 is the moment of that plastic alone, which is the net resultant of total plastic minus elastic, is it not? That is what M2 is. So, M2 could be sigma y of B h square by 4 minus B E square by 4. Do you agree? Okay. So, my total moment carrying capacity M is nothing but M1 plus M2, which is sigma y of B E squared by 6 plus B h squared by 4 minus B E squared by 4. Can I quickly simplify this? So, I can say sigma y of B h square by 4 minus B E squared by 12. Is that okay? Which I say sigma y of B h square by 4 1 minus E square by 3 h square. Can I write like this, which is my M, is it not? I will call this equation number, this of course 2, and call this as 3, 1 is here. Okay. Now, for a rectangular section which we are discussing, Zp is given by a simple equation which is A by 2 of y bar 1 plus y bar 2, is it not, which can be simply Bh by 2, that is my rectangular section. B and H are the cross sectional properties of my section. A1 or y bar 1 will be nothing but H by 4 plus H by 4, which can give me B H squared by 4. Is that okay? I have B H squared by 4 here also. Now, can I replace this equation as M is now rewritten as sigma y B H square by 4 1 minus E square by 3 H square, which can now be written as sigma y Z p of 1 minus this, which is M. Okay. We already saw in the previous step that I can replace this as MP, that is plastic capacity of the section, 1 minus E square by 3 H square, which is M. That is a very interesting outcome of the derivation. What is the inference which we derive from equation number 4? If you know the moment applied onto the section. If you know the bending moment coming onto the section, you can easily estimate the depth of the elastic core E from equation 4. You may wonder how. Look at equation 4, the variables are, let us say m, m, p, e and h, out of which for a given cross section h is known to me. For a given cross section, depth of the section is known to me for rectangular. Okay. E is what you are determining, agreed. M is known to you, okay, you know M, the moment coming on the cross section. Now MP by M is simply the shape factor, okay. So if you know the elastic moment in the cross section, which is nothing but simply sigma y zp by sigma y z, which is nothing but sigma p, sorry, zp by z elastic, which is what I call as shape factor. So I know MP also, okay. I can trace and find out what would be the depth of elastic core for a given momented in cross section, okay. Any doubt here? So the equation 4 can help you to estimate the depth of elastic core for any moment in the cross section M. Let us see what happens to this equation when the elastic core does not exist, it means it is fully plastic. Okay, it is fully plastic. So before that, let us try to find the shape factors for different cross sections which we are interested in. Let us say obviously we will take the rectangular section for the beginning. The cross section is known to me, which is designated as h as the depth and b as the breadth. We already know shape factor is the ratio of plastic section by elastic section modulus. Zp we already know is a by 2 y bar 1 plus y bar 2, which is nothing but bh by 2 h by 4 plus h by 4, which is bh square by 4, whereas the elastic section modulus for a rectangular section is nothing but I by y max, which is bh cube by 12 into 1 by y max is in my case h by 2, which gives me bh square by 6. I can find the shape factor as zp by ze, which is bh square by 4 into 6 by bh square, which will give me 1.5. What does it mean? The plastic moment carrying capacity of a rectangular section is 50% more than that of elastic, which is 1.5 times of sigma y of z. Is that right? So my moment carrying capacity of a rectangular section of a beam is 50% more than that of an elastic section. So, shape factor will give you an indication what would be the additional capacity of a section when you do a plastic design. The section is remaining same, I am not increasing the width and depth of the section, B and H remain same. Just by shifting my design philosophy from elastic to plastic, I get additional load carrying capacity in the section, which is a gain, okay, is it not? This for rectangular. Let us look at circular sections. Let us say the radius of the section is r. We already know the CG of the upper half, which I call as y bar 1, will be nothing but 4r by 3 pi, is it not, which will be as same as the lower section also, which will be y bar 2. Y bar 2 is also equal to 4r by 3 pi. So, I know the shape factor is given by a simple expression Zp by Ze, and Zp is given by a by 2 of y bar 1 plus y bar 2, okay, which is going to be pi r square by 2. Pi r square is the area of this section. Y bar 1 4r by 3 pi plus 4r by 3 pi. So, which will give me 4r cube by 3. Which will be Zp, okay. Z elastic I already know is nothing but I by y max. Y max in my case is r, I is let us say pi d power 4 by 64 by 1 by r. I can say pi by 64 of 2r to the power 4 1 by r. See, tell me what do you simplify this? What is that? Pi r cube by, no, you please check. So, can you quickly tell me what is S? Four r cube by 3 into 4 by pi r cube. Is it 16 by 3 pi? What is this value? What is this value? Is it 1.7? Huh? 1.16. Let us make it as 1.6. Okay. So, if you have a circular section, the plastic moment carrying capacity MP is about 70% more than elastic. Now, let us quickly compare a rectangular with that of a circular section which is solid, okay, solid. The moment carrying capacity of a solid circular section is larger than rectangular. It is because of this reason in marine structures people use circular instead of rectangular, because moment carrying capacity is higher, the plastic moment carrying capacity is higher. But commonly we do not use a solid section, we use annular, that is tubes. Now let us see what is the shape factor for a tubular section. So I call this as R2, this as R1, and of course this as T. Let us quickly see what is the moment of inertia of this section, which is pi by 64. d1 to the power 4 d to the power 4, which is pi by 64 2r1 to the power 4 minus 2r2 to the power 4 . So we get pi by 4 of r1 minus r. Is that okay? I call C equation number 1. So, we want to find Z elastic or Zy, which is the section modulus. I should say it is nothing but Ixx by Y max in my case is R1, yeah. So, which will be pi by 4 R1 4 R2 4 by R1, okay, that is my ZD. Now I am interested in finding out the y bar 1, which is Cg of this section, only this section. So what we naturally do is I will take a simple equation of A y bar by sigma A. If you want to find y bar, I should say sigma A y bar by sigma A and find y bar, okay, first principles. Let us do that here. So let us say pi r1 square by 2 4r1 by 3 pi minus pi r2 square by 2 4r2 by 3 pi, that is sigma A y bar, is it not? Sum of sigma A y bar, I put minus because it is an annular section, divided by sigma A, which is pi by 2 r1 square minus r2 square, okay, that is my area of this section. I am only finding out y bar 1, y bar 2 is below, that we will see later. Simplify this and get me what is the value. Which will simply turn out to be 2 by 3 of r1 cube minus r2 cube by pi by 2 of r1 square minus r2 square. Do you agree? That is my y bar. which can be written as 4 by 3 pi of r1 cube minus r2 cube by r1 square minus r2 square. Is that okay? I have just simplified this. Now I already know Zp. Zp is nothing but a by 2 of y bar 1 plus y bar 2. A by 2 is nothing but pi by 2 of r1 square minus r2 square, that is half of the area, with this 4 by 3 pi of r1 cube minus r2 cube by r1 square minus r2 square, the whole twice. Okay, let me put it 2 as I am multiplying 2 here. So this goes away, this also goes away, this also goes away. What is left over? Four by 3 of r1 cube minus r2 cube. Is it not? That is my Zp. I am looking for shape factor which is Zp by Ze, which is 4 by 3 of r1 cube minus r2 cube divided by, what is Ze? We already have in equation 1. Yeah, pi by 4 of, yeah, can you give me this? Is that okay? So I can say 16 r1 by 3 pi, simplify, 16 r1 by 3 pi r1 cube minus r2 cube by r1 4 minus r2 4. Is that okay? So let me say r2 by r1 be k. So S now becomes 16 r1 by 3 pi r1 of okay, which is 16 by 3 pi of 1 minus k cube by 1 minus k 4. Is that fine? So for k equals 1, that is r2 and r1 are same, that is solid tube, you will find not this, for r2 equals 0, that is there is no inner radius, okay, there is only one radius, you will get S as 1.698, which is same as solid circular. Okay. So what all we know is, if we know the shape factor for any given cross section, if I can find out the shape factor for any given cross section, I can always find out what is the enhancement in my plastic moment carrying capacity in comparison to that of elastic moment carrying capacity. What I wanted to know is only the shape factor. Okay. Many of the international codes for most of the sections, like a standard table shape factor is given. For example, I section, channels, angles, shape factor is known, it is a given data like an handbook. Okay. So, I can easily find out, select a section whose shape factor is maximum, so that I will get the maximum gain in my moment carrying capacity of the section. Okay. So, that is what we are interested in conveying today, that how one can find out the variation in elastic core in a given section if you know the moment at any section, number 1. Number 2, how plastic moment carrying capacity can be easily determined for a given cross section if you know the shape factor of a given cross section, which is a given data in most of the handbooks of steel codes. Okay. We have also understood that circular sections have more capacity of load carrying capacity in terms of plastic moment compared to that of rectangular, for which circular sections are more commonly used in marine structures, essentially tubular sections, but they have more capacity. Okay. Thanks.